So this paper is about soft prompt transfer, and it's called SPoT, and it's titled as SPoT Better Frozen Model Adaptation through Soft Prompt Transfer. So the main idea here is that we have some source task and we have some target task. So target task is our main task. So instead of tuning the prompts specifically on the task, what we are going to do is have some source or some different tasks which we call it as source task. Use those two source tasks to to get the prompts. Basically you prompt tune based on the source task, and once we have this ready-made source prompts, we use that to initialize the target prompts, and then we can use to evaluate um, on the target task. So how so we need some data set to tune this prompt, right? So we use either supervised C4, unsupervised C4, or we use one data set, one supervised data set, MNLI, or this is not S, this is or squad. Or we can what we can do is use the mixture of data sets to in some proportion to get the source prompt. So this whole first the half part of the image is the part one. Here they are showing the same thing. They have different tasks and they used it to prompt tune the source prompt, and these are 100 tokens which are prepended to the input sequence, and then they use this to initialize the target prompts. The second part of the so let's discuss the result for this one. So here you can see that the prompt tuning is independent prompt is being trained on specific target task. So there is no source task, only the target task, and you specifically train the prompts based on this. So here you get like 81 on super glue and super glue. These are average scores over all the tasks for glue and super glue. So suppose if you use source task with a mixture of all glue tasks and then you initialize it on the target task, you get this much, which is a little better than the baseline. But what's also interesting to see is if you just train the soft prompt using just one dataset like C4, MNLI, or Squad, you are still getting good performance. It's like good performance that the prompt tuning, and also for the superglue, which is interesting. But again, when you train it using superglue, it doesn't. It's like kind of same as the baseline. So, but I think the glue improves it very nicely. You can have a look on different combinations of the task and how they perform. So this was the first part of the paper where they introduced this method and the results. The second part is, suppose we have a certain target task, and we want to initialize it with a source prompt, but we don't know which source prompt or source task we should use. So they create a kind of a library where you have multiple source tasks, and based on the target task you can get the closest source task and use that to initialize the prompt. So how do they do this? So here in the image you have different tasks, and you have the source task embedding and source prompts. They make it into a library, and then based on the target task you query and you get the source prompt, and then you initialize the target prompt. This looks a little complicated, so let's go here and see how it works. So to see if the task prompts, so the task is similar to a source, we need some measure to see how similar they are. So what they're trying to do here is, so if we don't think about source prompt, just the target prompt, so we have this input, we have some source prompt, and we tune it on a specific task, right? So what they assume is that these prompts are can represent a task. So you can call these as task embeddings, because these are like specified for a specific task. So now specific task. So now that now at what point you're going to take it as task embeddings. So what they do is they pick a checkpoint at 10k steps as task embeddings. So you are going to prompt tune the prompt till 10k steps, and whatever is that prompt, you take that as task embedding. Now this will happen for every task, okay? So suppose we have a semantic space where each of the source is plotted using their source embeddings, and we have a target task. It will also have a task embedding, right? And then we are going to measure how similar they are with the source prompts. Now source task. So now they use two types of similarity. One, it's called cosine similarity of average tokens, and the per token average cosine similarity. It's about how they place the summation. It is inside the thing, and this is outside the cosine. So once you have some similarity, now you can pick, right? So they use three ways to pick the source task. Best of top k. So here what they do is, this procedure requires prompt tuning k times on the target task, once for each source prompt. The individual best result is then used for evaluating the effectiveness of this method. So we basically pick the top k and you train prompt tune it, and you find, oh, this is the best one, so just use it. The second one is top k weighted average, where you instead of picking one, you're gonna pick the weighted average of the top k source prompt. And then there is top k multitask mixture. We first identify the source tasks whose prompt are in the top k prompt and mix their dataset. So this is about like mixing the datasets and target dataset together. And then we perform source prompt tuning on the multitask mixture and use the final prompt checkpoint to initialize the prompt for target tuning. So this is how they find. So finally from here they find the final target, the source prompt for the target, not the prompt, is basically the source task embedding for target task. And this is what this figure shows. So here what's happening is, this is the so task embeddings are the earlier checkpoints. So these are like 10k checkpoints, and this is the best checkpoints. So this becomes the key, and this becomes the value. And then we have the embeddings. We will find closest source task embedding, and we'll find the best checkpoint for the source prompt, and then we initialize the target prompt. So what's the result for this? So the first result they want to show is here. So this is a baseline where they do the prompt tuning from scratch. There's no prompt transfer in this case. And they have different pick up, like how do you pick the source task mechanism. So this is one, and for different case. And what they find is, even for the k equals to 1, it's the performance improves 2%, around 2%. And as you increase k, it improves further. And same goes for this, the other method too. So that's kind of a gist of the results. The other important thing they discussed is about task embedding space. the semantic space which they build for the task embeddings. So what they are saying here is that these are good representations. I mean, the task embedding is a good representation of the task similarity. So the heat map is showing the cosine similarity. So the more similar the tasks are, the darker the boxes are. So then they clustered it together, and what they found was the data sets which are very close or similar, they are clustered together. The other important thing was, so this image, how do we read this image is, so these are source task embeddings, okay, and with respect to this data set, this is the target embedding, and with respect to this and the x-axis is the cosine similarity between these two. So x-axis represents the similarity, y-axis represents the improvement in the performance of the target task. So the more similar the task is, the more improvement it should show, right? So that's what they're saying, like they have some good positive correlation between how similar the task is and how much improvement it provides for the target task. So these are few results which was mentioned here. So yeah, it's an interesting paper, and you can go through for more details. Thank you.